Okay, so today's question is called dice coin paradigm. So it's another probability question. We flip a coin, fair coin until we obtain our first heads. Given the first heads occur with on the nth flip, we roll a fair six-sided die n times. Find the probability that the die value 1 is observed in the rows. So the minute we see, okay, we have something, we have n times and the n, then that means we definitely have to condition on this. So this question is basically testing our conditional probability. So I can break it down into the first part of the game and then the second part of the game and then just combine it together. And they're dependent on each other based on this n. So getting the heads in the first part, getting the first head would mean that in the front, everything up to that point was tails, right? I would have n minus one tails. I could have no tails and then straight get a head, or I can keep on flipping tails, and then my first head would be after all this chain of tails, right? That's the only way that could happen. And then for my coins, for my die, based on how many I have, then I could just use complementary counting. Like, I just count the number of ways that I would ensure I don't get that one. That means I have 5/6 of a choice, like 5/6. And then I would just 1 minus that to the nth power, so then I would get what I need. So essentially what I do is I condition on n. So the first part is getting to that n, the probability of arriving at that. So basically I just sum up the probability from getting one head, taking one turn to get that head, taking two turns to three turn, four turn, all the way up to n turns. And then technically this tells me that I did not read the question because n stands for a number of times, but my n technically is infinity in this case. So I did not read it initially, so that's why I wrote it in. But what it means in this case is that like I can go up to infinity based on the number of turns I have. Then once I can find this probability, then I can just define an event called HO, given n. So having one or not. So having one is true or not based on this, and what is the probability of this? So in the first probability of x equals n, so that getting that amount of um, turns to get that coin, it's 1 over 2 to the nth power. Why is that? Because we already talked about it has to follow this sequence, right? It has to be this. If it has to be this, that means that the first one has to be tails, the second one has to be tails, so on and so forth. Then we would have 1/2 to the n minus 1 power. And then the last one we know we have to get heads. So then that one also is 1/2 chance. So that our thing would just be 1/2 to the nth power. And then for the right-hand side, when we're determining the dice, given that it's n, we would have n of the thing, right? If all of them, in the case that none of them are ones, that means that we have 5/6 of a chance each time to not pick the one. So then for the n turns for each one, we would have that probability. So that would be to the n power, 5/6 to the n power. And then the case that we do have it would just be 1 minus that, right? The complement of that. So we can just take 1 minus this to be the probability. And then next we just, since it's multiply, we just combine the terms and separate it so that it's easier as an infinite geometric series sum. So we have 1/2 to the nth power minus 5/12 to the nth power. I just can put this 1 over n into the thing, and I just got those two. And then as n goes to infinity, we can just use the basic equation, infinite equation for geometric series to be 1, a divided by 1 minus r, where a is like the initial term and r is the common ratio. So inside here, our common ratio and our initial term is the same. So it's just 1/2 divided by 1 minus 1/2, 5/12 divided by 1 minus 5/12. Do a little simplification, we see that it's 1 minus 5/7, so we get 2/7 as our final answer. I think this question was relatively straightforward. The minute you realize this conditional probability and you condition on the cases that when it's going to be the case and realizing that it's a complementary probability, I think it's relatively straightforward. Okay, cool. That's enough here.